Welcome to Westel's Passive Components for Inquiring Minds. In this episode, we will discuss wideband interference filters. What is wideband interference? Where does it originate? How are the effects of wideband interference mitigated? Before the answers to those questions are revealed, two topics must be reviewed: filters and a high-level overview of how bidirectional amplifiers operate. Filters are devices that restrict or allow bands of frequencies to pass through them. There are four types of filters: low pass, high pass, band pass, and notch, also called band reject or band stop. Low pass filters allow lower frequencies to pass while rejecting higher frequencies. The filter's cutoff frequency determines which frequencies are considered low or high. For example, if a low-pass filter has a cutoff frequency of 861 MHz, then frequencies below 861 MHz pass through the filter unattenuated, while those above 861 MHz are attenuated. It is represented by this schematic symbol, or this one. This symbol shows two waves, with the top wave representing high frequencies and the lower wave representing low frequencies. If a wave has a line through it, those frequencies are blocked. Therefore, since this symbol indicates that low frequencies are allowed to pass, while high frequencies are blocked, it represents a low-pass filter. High-pass filters perform the opposite function of low-pass filters. They allow higher frequencies to pass while blocking lower ones. Bandpass filters have two cutoff frequencies. Frequencies between the two cutoff frequencies are allowed to pass, while frequencies below the lower cutoff and above the upper cutoff are blocked. Here, the schematic symbol has three waves: high, middle, and low. The high and low waves are blocked, allowing the middle frequencies to pass. Notch, band reject, or band stop filters are the opposite of bandpass filters. They also have two cutoff frequencies, but they block frequencies between them, while frequencies below the lower cutoff and above the upper cutoff are allowed to pass. The second topic to discuss before addressing wideband interference is a basic block diagram of a modern bidirectional amplifier. The first component a signal encounters in a BDA is a duplexer. The duplexer allows a specific band of frequencies through while blocking undesirable frequencies. We now should realize that a duplexer consists of filters. After the duplexer, the signal enters an LNA, low-noise amplifier. LNAs are great for amplifying weak signals. Most modern BDAs then will send the signal through an analog-to-digital converter. The digitized signal will then be processed by a digital signal processor, or DSP. The DSP is responsible for channelized filters, squelch, and channel gain. After digital signal manipulation, it is converted back to an analog signal by a digital-to-analog converter. A variable attenuator is used for the master gain control. From there, the signal is amplified to drive the antennas and then passes through a second duplexer. The chain of stages is duplicated for the signal's opposite direction. With filters in the block diagram of a BDA explained, we are ready to dive into wideband interference. In the United States, first responder networks use narrowband channels, typically 12.5 kHz wide. Cellular networks use wideband channels, typically 5, 10, or 20 MHz or wider. Wideband interference occurs when a cellular channel overwhelms the BDA with excessive power. This can happen when a cellular site is very close to the BDA's donor antenna. How likely is it that a cellular site is physically close to a BDA's donor antenna? Let's look at an example of an area south of Raleigh, North Carolina. The primary source of wideband interference is the FirstNet channel in band 14 of the 700 MHz band. It is broadcast by AT&T cell sites. Within this area, there are 15 AT&T cell sites. In that same area, there are no first responder towers. When we zoom out a little, we can find two. When a BDA is installed in this area, it will be closer to any one of these 15 cell sites than to a first responder tower. What happens to a BDA if it is too close to a wideband transmission? In this block diagram, the LNA and the analog-to-digital converter are prone to overload if a too strong signal is applied to their inputs. When overloaded, their outputs can be greatly distorted. Therefore, the lesser of two evils is to attenuate the strong signal to prevent the overloading. The attenuation may be placed in front of the LNA or the analog-to-digital converter, depending on the BDA's make and model. If attenuation is added to protect the circuit from overload, all signals, including first responder signals, will be attenuated. Because often the first responder tower is far away, these signals are weak to begin with, so the last thing we want to do is attenuate them further. It should be noted that programming the DSP not to amplify band 14 will not help the situation. The damage has already occurred before the signal is processed by the DSP. The wideband signal power required at the input of a BDA to initiate this attenuation will vary depending on the BDA's make and model. It is important to know this threshold when commissioning a BDA. A solution to prevent this additional attenuation is to block the wideband signal from entering the BDA's donor port. This is accomplished with a filter specifically engineered for this task. It is typically placed next to the BDA in the equipment room and cabled between the donor antenna and the BDA. Here is a spectrum analyzer screenshot of a wideband FirstNet signal. Nationwide, it is between 758 MHz and 768 MHz. Just above those frequencies are the narrowband first responder channels, ranging from 769 MHz to 775 MHz. Let's input all of this RF into a Westel band 14 filter. And this is what is coming out. Sweeping the filter with a spectrum analyzer shows band 14 below 769 MHz is clearly blocked, while the narrowband frequencies are allowed to pass. A question arises while observing this wideband signal on a spectrum analyzer. What is its power level? Simply placing a marker on the highest point will not measure the power of the entire signal, only the power within a small passband indicated by the spectrum analyzer's resolution bandwidth, or RBW. To calculate the entire signal's power, use this formula. In this example, the marker power is minus 48 dBm. Minus 48 dBm plus 10 times the log of 10 MHz over 100 kHz reveals the power the BDA will see is minus 28 dBm. If the spectrum analyzer supports an occupied bandwidth measurement, that can be used as well. Here is the same signal as seen on a PCTEL scanner. Is there a similar issue with the 800 band? That answer is a bit more complicated and also a lot more concerning. In the 800 band, the frequencies between 862 MHz and 869 MHz are known as the ESMR band. The ESMR band was used by Nextel, then Sprint, and then T-Mobile when those companies acquired the other. However, T-Mobile, the current license holder, has shut down most of its transmissions, as it was instructed by the Attorneys General to sell the ESMR band when it acquired Sprint. That transaction has not happened as of the time this video was made, in June of 2026. But eventually, that band will be purchased and transmissions will be reactivated. When that happens, all 800 MHz band BDAs that currently have no wideband interference issues could be driven into overload overnight. Filters like this Westel filter are perfect for 800 MHz only markets, as they not only block the ESMR band, but also the entire 700 MHz band. Here we see the 700 band and the 800 band channels entering the filter, and here is the output. To prevent potential issues in the future, it would be wise to install these filters in 800 MHz only jurisdictions. Thanks for watching this episode of Passive Components for Inquiring Minds. Be sure to view them all.